Okay, thanks for the introduction. So first of all, I would like to thank the organizer for giving me the opportunity to give a talk here. Yeah, in fact, it's being here remind me of a very pleasant time, as I say, 20 years ago, where I was here as a postdoc for 3 years. And I'm very grateful to Jakob for his support, also for his kindness during my stay and after my stay. So I enjoy very much being here, and I'm very happy to be here for your birthday, for this week. And so my talk is about Cuprate Superconductivity. Okay, it's a joint work with this gentleman here over there, and I have so this is working. Okay, this. Okay.
I know, now it's working.
Okay. Okay. You already changed.
Change?
Okay. So that is the pointer, and okay, that's more. So due to the lack of time, I have two parts in my talk. The first part is mathematical, but I will keep it as very short. Let's say something like 10, 15 minutes, not more. Because I would like to explain a little bit Cuprate superconductivity, and probably you don't know very well what is the particularity of cuprate or the physics of cuprate, and I will explain this in the context of the models that I am going to present just at the beginning. And in my talk, it was speaking about exchange interaction. I mean, I'm interested in a specific kind of interaction between particles. So it's between boson and fermion, and there will be typically a pair. So I have an exchange because I exchange a fermion by a boson. B is a creation or annihilation operators of a bosonic particle, and C would be a pair of fermions. So we have a pair of fermions which is destroyed and create bosons. So that's the exchange interaction that I am interested in, and I will explain later when I explain cuprate why I am interested in that kind of interaction. And from a mathematical perspective, this goes with a kind of delay when I, yeah. It's two individual fermions, but spin up, spin down, typically. No, not necessarily at the beginning. But I would explain how this exchange interaction make a bond state out of this. So I introduce here, this is, take this as a formal expression because, so I am in ZD, in the two-dimensional lattice, Z2. So everything that I am speaking about is on 2D. The models that I am interested in, so this is absolutely not, does not make any sense mathematically speaking, but nevertheless, it's just to give you what is the model that I'm interested in terms of creation annihilation operators. It is, so I would have three parts. I have a first part, which is fermionic part, another one, which is a bosonic part, and a third one would be my interaction between boson and fermion. My fermionic part is just this part here is just a second quantized version of the discrete Laplacian. So this part here is just a kinetic energy with a certain parameter epsilon. This part is just a Hubbard interaction. And so it's particle spin up interact with particle fermion spin down as the same latticite. And this is an extended, so to say, Hubbard interaction that I can add if I like, for free. So that's the fermionic part. The bosonic part is just the free bosons. So this is a second quantization of the discrete Laplacian on the two-dimensional lattices expressed in terms of a bosonic system. And my exchange interaction that I've presented in the previous slide is just something like that with a certain coupling Vx minus y. And this, I destroy a pair, which is not necessarily on the same lattice side. We could have x plus z and x plus z and x, and z is something with a certain coupling pz, and which is destroyed and create a boson, and the other way around. Yes, up-down interaction. Yeah. So mathematically, so I will have two slides for mathematics, this one and the other one. What we did, mathematically speaking, is you take the models that you have seen formally, you restrict it on three-body problem. Let's say two fermions of opposite spin and one bosons. You restrict this. This defines a correct Hamiltonian, which is well defined, whereas we have a fermionic part and a bosonic part. This Hamiltonian is translation invariant. He has some certain symmetry. You can decompose it in terms of quasi-momenta. So that is this decomposition. This is a fiber Hamiltonian attached to this up to some unitary transformation. So this is the Hamiltonian which depends on the quasi-momenta, and K. So I have a pair of fermions, so two fermions, one bosons, and K is in fact the velocity, the quasi-momenta of the pair of fermions. The pair of fermions has a quasi-momenta, and then there is a relative quasi-momenta with respect one fermion with respect to the other one. So there is two components. There is one component. This is fermionic part. This is bosonic part. The fermionic part still act on L2 of the torus minus pi pi, and this is just a complex number. So if you take the models that you have been before, you do this restriction and you compute what is this kind of this expression. You have explicit expressions that I don't want to explain or you get it.
So in this matrix,
Yes, because U is related to the Hubbard interaction, and this is only the fermionic part, and it's only fermion with fermion. Where is where this has just to say this is a bad notation. This is a unitary transformation.
It's okay. So,
Is a number. It's a Hubbard interaction. It will be important when I explain about cuprate. So the only mathematical results that I would explain you is to know what is the spectrum of these guys here for each fiber. So the spectrum. So this is this theorem. Where is something to write? A of u, comma k is this fiber Hamiltonian here. It's not a function; it's an operator. So this is an operators which act on L2 of the torus and just direct sum with the complex number.
Dependence on U.
It's not written. There is a density, so you get a U and a certain projection. If I didn't want to enter on the details of what is this, because otherwise I do not have time to explain why this model could be relevant. So the spectrum is, if you look in one direction, alpha k, for example, typically one direction will be important in the torus. So torus between minus p minus pi square. Then the spectrum is as follow. You have something like that. So for each alpha, so with a certain direction k, here you have something here. Here this is essential spectrum with here, and here you have a certain E alpha k. Okay, I can keep U if you like. Alpha k, which is an eigenvalue. It's bond state that you have here. You have an eigenvalue here. And which a certain wave function attached to this eigenvalue. And what does the eigenvalue mean? You get it's a bond state. It's a pair of electrons which are bound via bosons.
So capital K
is one specific K.
K
belongs to the torus.
K equal.
Yeah, it's just one example.
So it belongs to.
No. It's one choice. It's one choice of K. I mean, it's just to make, I cannot make the pictures for all K. Just one choice.
Yeah, one choice that you should belongs to, not equal.
But this belongs to the torus, and this is just 1, 0 pi.
0 pi, okay.
And so here it's alpha pi, so to say.
Okay.
And I draw with alpha.
0, alpha.
Yeah, 0, alpha pi. Yes, you're right. Okay, so what this means? So you can prove that there is this kind of bond state. It's a pair of fermions dressed with bosons, and they form a pair. And you can analyze what is the eigenfunction of this. So this is related to a certain eigenfunction, which is something like that. This would be an eigenfunction. It's a non-degenerate eigenvalue, which is a unique eigenfunction. This is fermionic part. This is bosonic part. And you can, for example, if you look on the X space, what is this function? It is exponentially localized. So it's represent a pair of electrons which is exponentially localized. So they are close to each other, and which are bound via a certain bosonic particle inside. Okay, so that's what the exponentially localized is. Here you can analyze, so there is a gap, in particular, there is a gap here. There is a gap here. And this gap can be uniformly bounded with respect to the Hubbard interaction. Yeah.
I understand. So your model had terms where you create simultaneously a pair of fermions.
No, you take two fermions, yeah, and it destroys one boson. You take two fermions, they are destroyed, and they create one boson. And you have the complex, the self-adjoint conjugate of that, which is.
Okay, but your Hilbert space is now, you look at the situation where you either have a pair of fermions or a boson.
Exactly. So direct sum.
This is the matrix structure.
Exactly.
That's the okay. So
Exactly. No, but it's normal because I did not give any data, so it's difficult to catch up this information. Okay, so from this for the fiber Hamiltonian, you can deduce a property of the spectrum of the Hamiltonian itself. So this is that corollary. I don't want to to go. So, yes.
You have a gap
In the limit u to infinity, yes.
No.
This one. Yes. 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 Yeah, it's just because the exchange interaction makes this bond state. And the U can only be a problem because it can destroy the pairs, but it's allowing to have a pairs which is not on the same lattice site. And so if U is very big, it does not destroy the pair. Huh? It does not change anything because what makes the pairs is the exchange interaction with boson and fermion. So U has no effect. Okay, so let's go to Cuprate superconductivity, and at the end I will explain what is. Yeah. Yes. No. It's true that you have an eigenvalue, but the eigenvalue is just the one which corresponds to the bosonic part, and there is no connection between both. There is not this description that I am speaking about vanished. So about superconductivity, let's go a little bit fast because I will have not enough time, I suppose. So it started in 1911. So there were a discovery of mercury in 1957 with the Dyson famous paper, but there is also a BCS theory for conventional superconductivity. And a breakthrough was in 86 with the discovery by Bernoulli and Müller of ITC superconductors, and they are done with cuprate. And it was Nobel Prize in 87. And nowadays there is many superconducting material. There is various type of superconductors. But one thing which remain, theoretically speaking, is this ceramic material, this cuprate. I mean, there is no consensus really about the microscopic theory of this material. There is many community or sub-community which thinks that with the TG model, with spin, blah, 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 they can do it. Other one use electron-phonon interaction, but there is no consensus out of this. So, what is? So first of all, why I stay on 2D? So I say my system was 2D. It's not because I cannot do it in 3D. I mean, mathematically speaking, I could do it in 3D. But why I explain about 2D is because the cuprate, all this cuprate has one particular phasor. It's that they are made, or they are layer of copper and oxygen each time, and the superconductivity lies in this layer. So the superconductivity are on the special layer of copper and oxygen. So that's why I restrict on 2D. One thing maybe you would be interesting to know is so let's forget about what is written here, but looks, for example, on this phase diagram. So how do you get a cuprate superconductor? At the beginning, you take a cuprate, usual one. Usually it's antiferromagnetic at low temperatures, and it's a mode insulator. So it's not metallic, nothing. It's a mode insulator. So this is one famous cuprate here that we have here. And so at the beginning, if you below the temperatures, then you get an antiferromagnetic phases. So what they did, they as you do for semiconducting material, they dope it. They do a doping. And for example, in this case, they add this atom here, strontium, I think its name. And by doping it, so at the beginning you have a mode insulator. So that means that each lattice site, for example, on your two-dimensional layer, you have an integer number of electrons typically, or all. So adding a little bit of doping, you add extra hole or extra electron, depending what is the doping, and this breaks these mode phases. And rapidly, the antiferromagnetic phase rapidly disappear, and after a certain doping, then you get a superconducting phases. So it becomes superconductor. And there is a special also, so that's the critical temperature of the superconductor air, and then there is also something which happened, which is a pseudo-gap regime. And it is, my model is more designed to this regime than to the superconducting phase itself. And the superconductor, the pseudo-gap temperature means that there is uncertain, if you make analyze the excitation spectrum of your system, of your pairs inside your model, you realize that there is a gap in certain for particular quasi-momenta. In particular, for this kind of momenta, 0 pi. This is when the gap appears. So, and it appears at very large temperatures as compared to the superconducting temperature. Okay, so now let me explain a little bit more into yes. Mm-hmm. That is a purely electronic explanation, and what I am going to explain, at least from a lot of experiment, is that there is an important part which should play a role, which is a polaronic part. So bipolaron that you are talking in is important in that things, and experimentalists claim that you cannot explain superconductor without involving this bipolaron, which is more or less for a certain part of the community, which is removed from the scene to explain superconductivity. And so it's what I'm going to explain. So here you have a two-dimensional lattices. Here there are copper, and here there are oxygen, which is air. And when they discovered superconductivity, in fact they haven't done this blindly. When they did that, they wanted to use a so-called Jahn-Teller effect on coppers. The Jahn-Teller effect is when you have a degenerate ground state. The degenerate ground state is not stable, and there is a spontaneous symmetry breaking which break the isotropy of your system. And breaking the isotropy of your system, it distorts the lattice. It makes a distortion of the lattice, and it creates, in fact, a polaron. And so the copper it was designed when they found ITC superconductivity. They wanted to use this to have a strong, for example, electron phonon mechanism to get a superconductor. And so that's what's happened. In fact, that there is a formation of polarons, as they found experimentally. And there is one additional thing is that it's antiferromagnetic, and they show in experiments that there is still antiferromagnetic correlation even if the antiferromagnetic phase disappear. And if you have a polaron which is only when spin up, which appears, it breaks. It's difficult to move, and it turned out to be favorable to get a bipolaron. So two polarons which are created at the same time, and with spin up and spin down, and which is well adapted to an antiferromagnetic correlation because they are up and down. So that makes. So what, for example, some group of experimental physicists like Müller claims that there is evidence, not only an evidence for them, it's clear that there is a formation of bipolarons in that kind of system with spin 0. So the idea behind this exchange interaction is the following. You have a pair. The pair is moving on the lattice, and so it is moving. It is shown experimentally that it is moving within the oxygen, not within the Cooper. And sometimes it gets trapped and form a bipolaron. And sometimes it is released. So they also estimate that the bipolaron are not stable. They do not stay forever. They are relatively unstable. So your two electrons get trapped, and then you get a bipolaron. That would be you could modelize it as a caricature as a bosons. And sometimes they are released, and then you again have a conducting pairs, which is moving. So that's the pictures. So here, what I am saying here, so it occurs only in oxygen atoms. So bipolaron have zero total spin. I already say that. Experimental evidence of short lifetime of polaron and cuprate decaying in two fermions. So that's three facts that I already mentioned. So some people think of that. Okay, you have bipolarons, so maybe you have bosons. So of course everybody knows that boson can condense, and so maybe the superconducting is a Bose-Einstein condensation of bipolarons. There is some people, a small group, not a big group compared to other group of theoretical physicists, but which was thinking of bipolaron as being the charge carrier of my superconductors. There is one problem of this, is that they have an effective mass which is large, these bipolarons. So they hardly move. I mean, it's not very, it's not likely that they would be the charge carrier. I mean, they have a large effective mass, and also experimentally, they are able to show that with two types of particles. There is one of polaranic natures, which will be these GT bipolarons, and another one which are mobile, which are much lower effective mass. And that would be interpreted as free or pairs of fermions moving around. And so that's everything is to explain you why I am interested in this exchange interaction between bipolarons and pair of fermions. And so that's why I wanted to understand what is doing, mathematically speaking, on a simple model. I am not able to do the many body. It's too complicated. There is already the Hubbard model only with this, and I'm done. Cannot do nothing. So on a three body, to look what's going on if I have this, and what is physics that create for this simplified model that I know that I could solve mathematically speaking. And there is one thing that we should not avoid, that was where this U at the beginning is, because these systems are strongly correlated. If there is a mode phases, if there is a mode insulator, it means that there is no itinerant electrons that don't want to move. It means that the Hubbard interaction is sufficiently strong. So you in your pictures, the Hubbard repulsion should not disappear. Should be there, should be taken into account. So that refers to that thing that I am speaking about. This is quite important if you want. If you don't have this, then you don't get the results that I am going to present at the end about quantum real prediction. Another thing which is important is, how do you prescribe this V? So from now, I am going to explain how I fix all my parameters and how I produce a quantitative result out of this. So the first question, if I have this, is how I can prescribe this function V, which looks like a nice abstract mathematical function, but I would like to know with respect to cuprate how this function looks like. And so there is property about phonon excitation. So this is related with phonon excitation. And there is two phonon anomaly in this, and this phonon anomalies, there is a phonon anomaly for two kind of quasi-momenta. This one, 0 pi or pi 0, which was my example here, and also 0 pi over 2, plus or minus. The origin of this anomaly are different, and this one can be explained by density functional theory without any problem. Whether this one cannot be explained by density functional.
What is an anomaly?
So there is two different kind of anomaly. This one, if you increase the doping, the energy of phonon vanish, decrease. But the decrease of this phonon energy is much stronger when you reach 0 pi. So it decreases much faster, like if you have something which goes down. This is one anomaly. The second anomaly is this one. It's related to what Valentin said on Tuesday about the spectrum of the Bogoliubov spectrum. I mean, you do you perturb with a certain momenta k, like a diffraction, and then you measure what is the outcome, and the outcome is not a sharp peak on one thing. He has a certain how do you say yes width a certain width, and it becomes very large when you reach this. So it's two different kind of anomaly which you have here. And since density functional theory, from which there is no creation of quasi-particles, is taken into account, predict this, but not this. What is expected, one hypothesis is to say that in this particular things, what happened is a creation of bipolarons. That means that my function v here, if I take the Fourier transform of v, which is a function of quasi-momenta, it should be maximum when you have this point here. It should be peak at this point. It's exactly what we did. We did this function v, the Fourier transform of v, being peaked at this point, 0 pi or pi 0. One thinks, I don't know how much time I have. I hope I succeed to. Yeah, okay. We will see. Another thing which is very important for cuprates is that they are D-wave superconductivity, mostly, but not in reality, not only exclusively D-wave. But there is a D-wave symmetry. So to explain you what is D-wave symmetry, if you have a wave function which is L2 of Z2, you can decompose this function in three parts. One is S wave, the one is D wave, and the other one is P wave. What is your definition of S and P and D? S wave is a function which is invariant for any rotation of pi over 2, pi, 3 pi over 2, and of course 0. So about this group of rotation, it is invariant. D wave is the one when you do a 90% rotation, then you get -1, and then it's symmetric, and then -1. And P wave is a wave function when you do a P rotation, so 180 degrees, you get -1. So any function A, it's easy to see that any function A can be separated in three parts. And so as a fact, in cuprate, the wave function, the macroscopic wave function that you have are D-wave characteristic, but not exclusively D-wave. The estimation is something like 70-80% of D-wave and 20-30% of S-wave. So that's something which is I mean, if conventional superconductivity, they are S-wave. In conventional superconductivity, you don't have this phenomena. Okay, so so let's come back. So I took again the same model. Here I remove the extended Hubbard interaction. I have the fermionic part, the bosonic part. I have the exchange interaction. Now I know that the Fourier transform of V should be peak for 0 pi and pi 0. I have many parameters to fix. I would have to fix what is epsilon here, what is HB here, which is HB epsilon. It's is related to the kinetic energy of the bosonic part, and also even if I know that this is peaked, I should know also its strength. It could be peaked, but it could be the peak could be at 0.1 electron volt, or it could be 10 to the power minus 10 electron volt. I should have also its strength to be fixed. So you can fix this. You can fix this using the effective mass of all. So that you can take what is experimentally measure, and you can fix what is this. You can fix also the effective mass using the effective mass of bipolarons and the lattice spacing of your system. U, how do you fix U? U is when you have one hole on one oxygen, one hole on one oxygen. The oxygen is O minus minus. So if I have one hole, it's O minus. And U is the difference of energy when you go from one hole to two hole. So it's and when you have two hole, it's a neutral state. So oxygen. So this is called the electronic affinity of the oxygen. There is table which are known with precision, and you take this number, which is, if you want to know, it's 1.5 electron volt. This is 0.266. This is 1.5, so it's 5 times bigger than this one. So the Hubbard interaction is strong. And it remains the strength of the function V, how strong it is. I know that its peak for its maximum value is for 0 pi or pi 0, but I would like to know what is this value. So we did it by using a paper in Nature saying that there is a 90% depletion of electron in comparison to the doping that you get. There is 90% depletion. Using these things, you are able to fix. So what is the depletion? So what will be our estimate? You take these guys here. You compute what is these things here. You have your wave function is this here. So the question that you ask is this what is D wave, S wave, P wave? This is question. Using the parameters that I can fix. Using the parameters I can fix, I can make numerics to estimate exactly this, that, and to know if it's P, D, and S wave. The depletion, it is written here. It's a proportion of fermions of all which are on really to all with respect to the all norm of that vectors. That will be the depletion. So that is this equation that I have here. And you run numerics, you run your stuff, and you see that to get 90% of depletion, you see a certain kappa, which is in concretely 0.11 electron volt. And then you have fixed all your parameter of your model, and I have the mathematics which tell me how it works, or I can solve it and compute it. And so what is the prediction that we get is, so using this, we get 60% of S wave, 83% of D wave, and 0% of P wave. And the 0% of P wave is not numerics, it's completely rigorous. You can mathematically prove that P wave does not exist. By the way, just a slight comment, D wave, it's an anisotropy, because when you do 90 degrees, you have minus 1. But my model is not an isotrope. It's an isotrope model. Huh? There is no ad hoc anisotropy add to my system. So experimental data says it's 20-25%, 75-80%. This is crude estimate, and here 0% of the wave. So the pseudo-gap temperature, so if you analyze the gap here, you compute what is the gap here. So the gap here, if you compute, if you express in terms of Kelvin, it's 1,250 Kelvin. It looks huge, but this is not that huge, because the experimental data says that the pseudo-gap temperature, so the pseudo-gap is when, or you see the pseudo-gap, is when there is pair which can be produced without being stable enough to get a collective phenomena and a superconductor. Yeah. Yes. Fermi temperatures. I don't have any Fermi temperature because I don't have any temperatures. Because I analyze. Yeah, because I replace this in joule or electron volt in terms of using multiplying with the Boltzmann constant to get the temperatures. But it's just an energy. I have two fermions.
Okay. So
it's two. It's solving the tree body. That's why I yeah. And no, because I have only two fermions. Yeah, no, for me. Yes, exactly. Exactly. I have something. It's a single pair. You have a pair and you have a boson, and you want to see how they are likely to bind themselves. It's a way here. What is adapted is not to explain, to get the collective behavior, which will be the superconducting phases. That will be the collective behavior. Is to see in my system. That's why I insist about pseudo-gap temperature and not the critical temperatures. It's all likely when you have two electrons, and all likely they will bind to do these pairs. And then if you think about your system, you can have many pairs which are destroyed and created, and if you go lower in temperature, then they will form a collective behavior. At the beginning, they just bind together. Yeah.
So, but
yes,
so
yes,
I was
yes.
wondering what happens.
I mean, I'm not in k equals 0. I'm in k equal 0 pi.
Yeah, but then you don't.
Yes.
So I was wondering if
this I cannot answer that question up to now. This I don't know how you will modify this. I considering. I mean, this is out of the picture. I just want to fix what is the probability to get this, and what can I extract from this? Just this information. It will. It would be above the Fermi surface, where there's only conducting part that these pictures start to be relevant outside.
even if you don't think about
Mhm.
then
It's what the things tell you. I mean, there is, the V, the coupling is completely isotropic.
But you add then isotropy.
No, I don't add any anisotropy. I don't add any. It's come out because it's because of the strong Coulomb repulsion. If it prevents the two fermions to be on the same lattice side, they have to be here, and then it's more favorable to have D wave. This plus Hubbard interaction. The Hubbard is important. Without the Hubbard, you will get S wave. If you don't have Hubbard, a Hubbard interaction, you get S wave. The kinetic energy just create a little bit of S wave and destroy a little bit the purity of this D wave. It makes it's in some sense opposed to the Hubbard interaction. Okay, so maybe I should stop. So let's just finish to say that you get this binding energy, and about covalence lengths, you get very good agreement with experimental data because you get 1.6 nanometers, 2.1 in another direction, and the experimental data is between 1 and 4 nanometers. So it's very accurate. With respect to experimental data that we get, so it's a caricature. I agree, it's a caricature. It's too, but it gives very good outcome in terms of even quantitatively out of this. Okay, so I stop here because my time I think is by far gone. Thanks a lot, and congratulations.